So, welcome all to a tutorial based on the week 1 content covered in the course Introduction to Machine Learning. Just to confirm, am I audible properly to all? You can type it in the chat box if I'm audible. Any one of you, that would be fine. Okay. So, this is not a regular class on this course, but a tutorial session. Here I would be discussing past year's questions that were asked in assignment. So in your course, you see an option of assignments, right? So I would be discussing past year questions just to make you comfortable with how to attempt this year's question. Also, I would be try to just cover the basic concepts that were covered in the class, so that if you have any doubt, you can ask. Right now, I have disabled a mic option for you. If you have any doubt, you can type it in the chat box, and I can enable the mic for you if you want. Then, so today I'll try to cover 3 broad concepts. First is what are different tasks, or what are different types of machine learning, right? So whatever I'm covering is based on whatever was covered by Professor Sudeshna Sarkar. Ajay Kumar, this is not the first class. If you are joining this, you are expected that you have watched first week of the lecture posted on NPTEL or swayam. And this is just a doubt clearing session, more of a doubt clearing session. So I have kind of divided my session in 3 parts. First is different types of machine learning. Okay. So second part is the loss functions that are important for machine learning. So different tasks have different kind of loss functions. So second part is loss functions. And third part is bias and variance. So these are the 3 broad topics that were covered in the first week of this course. So if you have any doubt related to content, what is taught in the lectures or anything that I'm saying, you can just type in the chat box. One request, whenever I'm covering different type of machine learning algorithms, if you have any doubt related to that you can just ask then and there. So what I want is doubts related to a certain topic should be asked within that time. So Ajay Kumar, you can register for the course on swayam, and there you will find an option to watch all the videos. And yeah, that is more exhaustive content, and this is just a doubt clearing session. So to begin with, I would want you to answer me, what do you understand about machine learning? What do you think machine learning is? So then I'll give my opinion. Machine learning is for me. Can you please type it in the chat box what machine learning is for you? Whatever you think machine learning is, you can just type it out. Okay. Making the machine to learn, right? So when you see a child grow, right? He automatically, not automatically, but he sees people are walking around him and he starts walking, right? We don't explicitly teach him that he has to lift his foot and move forward. So from his experiences, he learn how to walk. Now, if you want a machine to perform the same, it is very difficult to explicitly code, you have to move your feet, then move down. So this kind of algorithm is very difficult to model explicitly. So machine learning is nothing but giving the ability to machine to learn from its experiences, whatever it sees, whatever is fed into it. That is what is machine learning for me. Right? Most of you were correct with your answers. So some of the common tasks that machine learning does, in today's context, and this list is not at all exhaustive. So there can be many tasks that you might know, or there can be many tasks that people are doing. But broadly, these are the tasks that machine learning models do. So first of all is classification. What classification is, given an input, you have to assign that input to a certain class. For example, let's say I have written 1 over here. Your mind can easily read that it is 1 written over here, right? But if you want to ask a machine, then that kind of task would be a classification task. That machine has to classify it from 1 to 9. So this kind of task is called a classification task. Another example would be image classification task. That is, you are presented with the image of a dog, let's say, right? Then you know that it is a dog. But how can you train a machine to do that? That would come under the task of classification. So this first week content is just an introduction to what we are going to do further in the course. So I won't be today teaching you like how this classification task would work, but I'll just be introducing you what is a classification task, right? Now, the second kind of thing, the task that we do is regression. In regression, what we do is like in classification, for every input, whatever input we were giving, we were assigning it to a certain class, right? Now, in case of regression, what we have to do is rather than a class, we have to assign it a continuous value. Okay. So in regression, we want to assign every input a continuous value. For example, uh, yeah, it is fine. For example, uh, just a second. For example, you have something like you have a house prediction task at hand, the price of a house. So you want to sell a house and you want a machine learning model to predict for you what should be the best price for that house. So you can give as an input the size of that house, the area in which it is located, and then you expect the machine learning algorithm to return you the price. So this price component you see is a continuous thing. You don't have classes over here, like you don't want it to like give you values that it should be between $100 to $200. This shouldn't be the price of a house, but yeah, this is just an example. Or something like 200 to 300. You want the exact price. So this kind of things comes under the regression. Another example can be when you use Google Maps. It gives you an estimated time of arrival. When you search any place that you want to go there, then it gives you an estimated time of arrival that you would reach here by this time. So those kind of analysis are done by a regression task. Another task is something called clustering. Over here, what you want to do is you have data given, then you want to cluster them or group them together. This voice issue, is it for everyone or is it clear for others? I hope it is clear for others. Okay. So clustering is grouping data, right? So I'll draw just a simple example. Let's say you have something like this, right? You have some points here and you have some points here. So if you see by naked eye, you can figure out that this is a group of data points and this is another group of data points. Teaching machine to identify two different groups of data points. This is something called clustering, right? Another interesting task is something like machine translation or language translation. So you go to like Google Translate, you type it in one language, it outputs you in other language. This is something called as translation task. So this won't actually fall into any of the above categories. So this is another task that you can do. Another task that you see is when you start typing something on your mobile phones, then sentence tend to get automatically completed. So this kind of task also is another common task in machine learning. So through this course, you should be able to, at the end, you should get an idea how would you able to make this kind of task work via a machine. So any doubts till now, you can just type it out in chat because this is a doubt clearing session. You already have learned these things in the like lectures. You have anything to ask, you can ask here related to this. Okay, I'll move ahead. So if we talk about type of machine learning, this type is not exactly like defined properly, I would say, but people tend to categorize them into these categories. So there is no like definition that the complete set of like machine learning algorithm can be divided into 4 parts. There are many types of machine learning algorithm, but broadly what we study are from these categories. So first of them is supervised learning, right? What we do in supervised learning is what you have, like first of all, as I mentioned, in machine learning, you have some data points, and you use these data points to get some output, right? Those output can be different cluster, or those can be the classes that you get, or those can be regression values that you get. So in supervised learning, the data that you are given are like you have some data, features corresponding to some data. What I mean by a feature is, let's say you want to predict gender of a person looking at his photograph, probably, right? So this photograph is the data that you need to input to the machine learning algorithm. So here you have the data, the features that you have. You need to provide the feature to the algorithm, as well as the true label that you have to provide. So remember, when you were a child, somebody might have told you that that is a dog. That's how you learn to recognize that it is a dog, right? So here also we need to give the computer pictures of, let's say, dogs, and tell him that it is a dog. Then he will process many of these data, and at the end he'll learn that these are dogs. Now in future, when you will input similar photos to that machine learning algorithm, he will learn that he will output you that this is a dog, right? So this kind of setup is called supervised learning, where you initially give features as well as the label to the algorithm to learn, right? So these kind of things are called supervised learning, right? So an example can be image classification, right? So the example that I discussed, right? Next is the category of unsupervised learning. In unsupervised learning, you don't have labels available with you. Okay. So you just have the features available with you, but no labels. Labels are not there. So here you have to work without the label. So some kind of task that you can do without the label is clustering or the grouping these data points together, as I mentioned. So Ankit Singh, regression are not only linear. So let's say you have something like this. So you want to fit and curve to this, then you can have a polynomial regression also. Some people also use like combination of sine and cosine. So it is not always linear, but linear is a very good starting point to study, and any problem can be molded as a linear regression. What I mean by that is, I'll just throw some light over here. So let's say you have some x, right? And you want to predict y corresponding to it, right? So this would give you an linear combination between x and y. Now, if you, rather than using x, you square every of your data points, then what you have got? You have got a feature x square, right? Now, when you draw x square versus y and you use linear regression, you will get a linear curve, right? If you are using just the linear regression with respect to x. But when you draw this curve with respect to x, then you would have got a like quadratic polynomial in your hand, right? Do we need programming knowledge for this course? So this question, I think you should post it in discussion forum, because I'm not an officiality of the course. I'm just here to take the doubt session. So you should post it here. But machine learning, I think you should start doing some programming. That would be more beneficial for you rather than just looking at the theory. Nobody would stop you from doing the course, but yeah, like having some programming knowledge or gaining some programming knowledge would be more beneficial for your benefit only. So I think that linear regression thing is clear. Okay. Now, if I go to this unsupervised setup, so in unsupervised setup, you don't have labels available with you. Okay. So there you have only features, and the kind of task that you do is clustering. Right. Clustering is one of the examples. Next, I move to the task called reinforcement learning. In reinforcement learning, what we do is we have an agent. Let's say I would like give an example over here first, and example can be thought as a definition. That shouldn't be correct, but yeah. So let's say there is a newborn baby. He comes to the world and he sees the environment around him. So he interacts with the environment. Now he sees that people are speaking, right? Or people are sitting down. Initially, the baby always keep lying. So he always sleeps, wakes up, then also is laying. So when he wants to sit, then he'll try some actions. Like he'll try to fold his leg. So after folding his leg, he will see how the environment is reacting to it. So the gravitation will play some role in it when he is trying to stand up or trying to sit down. So he will modify his actions according to the response that he gets from the environment. So this kind of learning, we try to mimic this kind of learning for the computers also. So we let the computer explore the possible options, right? So we let him choose what he wants to do, and whatever he chooses, based on that, we give him some reward or the punishment. And this he then and his objective is to try to maximize the reward and minimize the punishment or the loss that he's getting. Okay. So this kind of learning is called your reinforcement learning, and this is kind of very active area these days, and these are being used in something called driving cars, self-driving cars, or the automated drones that you see, or many other applications also. This is a like hot topic, but I'm not very sure whether this would be covered in a lot of detail in this course. So, okay, so I have covered till here different types of machine learning. Any doubt till here? Okay, so in unsupervised learning, what happens is like Indranil Roy is asking a question. So, what is the difference between unsupervised and reinforcement learning? In unsupervised learning, let's say this is your machine learning model. Okay, you will pass it all your data that you have. Okay, all the data you have, like let's say this is two groups that are being made, this graph. Okay, so if you pass just one data point at a time, then the machine learning algorithm won't be able to tell you anything about this point. You need to provide the underlying data structure. Then it will look at the data structure. It will try to uncover the data structure that is there. So this kind of thing is done by unsupervised learning, right? So, and in reinforcement learning, what happens is that algorithm will see his locality, and then he'll take one action based on many actions that from the many actions that are available from. To give you an example, let's say we have a self-driving car. Okay, it has a camera fitted to it. It will look at the scenery ahead. Then it has many options, right? It will go ahead. Okay, it can decrease the speed. It can like turn left or right. Okay, and another option can be to just apply the brake. It has some person in front of it should apply the brake. So it has to choose from one of these options. Now when you see a self-driving car on the road, that is a trained machine learning algorithm. So whatever we would cover in this course is about how do we train these kind of algorithms, right? So when we are training, we will allow this like agent or the car to take any of these actions, and based on his action, we will assign him a reward, like you have done it good, you have performed bad over here. So this algorithm then will try to maximize his reward, and based on this rewards that he gets, he'll try to learn the action, like what kind of action should he take when he encounters certain situation. Is the difference clear, Indranil? Okay. So right now I have, okay, how will reward benefit the programming? Okay, I'll come to that. So when you try to program these kind of things, uh, so I'll tell you rewards like what. So when we try to program these kind of things, so the kind of common program structure, I would say, or a common algorithm or agenda that most of these machine learning algorithm follows. I'm saying most of these, not all. What they try to do is they have some loss function associated with it. Okay. So you might have, all of you would have passed class 12, right? So in class 12, if you had a function, you learn to minimize that function. Okay. Minimize and maximize that function. So how do we program this kind of thing? Is we program them to minimize the loss function. So you ask like how would this reward benefit the programming? So the programming is nothing but a program to maximize the reward function. So based on the rewards that it is getting in every step, we define a cumulative reward function. And the whole goal of the code or the program that we write is to give us the exact steps that would maximize the overall reward function. Uh, so yeah, so you can increase that function. How can we meaning error getting minimized? That's correct. So like how can we reward or punish it? Like if that program is not behaving properly, you increase that loss function over there. So in next section, I will be covering some loss functions. It would be more clear then, I guess. We want to minimize the error or the loss. So maximizing reward is same as minimizing the error. So any doubt in types of machine learning? Like is it clear for everyone what is supervised, what is unsupervised learning, and reinforcement learning also, like what it is? I hope so. These are some questions from previous year's assignment. I won't be answering them. I want you to answer this based on whatever we have discussed till now. So this would be beneficial for whatever assignment you have to do. So this assignment that you have to do is your graded assignment. So this will help you like attempt those kind of questions also. So you can type in the chat box, like this is the first question. Which of the following is not a supervised learning? Not a supervised learning. So what do you think is not a supervised learning among this? Option C, correct. Yeah. So this is clustering is not a supervised learning. So clustering is unsupervised learning. So next question is the font, if it is not visible, I'll zoom it a bit. Yeah. Which of the following is correct for reinforcement learning? Okay, we can, let's say, algorithm plans a sequence of action from the current step. So let's say, this would be available, yes. I would be posting it on YouTube. So this NPTEL team will share a link most probably. Okay. So this is not a lecture, actually, this is a doubt clearing session. So you may not even look at it, that's your choice. Yeah. So yeah, so the algorithm plans a sequence from the current state. Okay. So like if you look at a child, like when you were 1 year old or 2 year old, did you know that what you would be doing 20 years later? So you don't know those kind of things, right? So like it does not plan all the steps from the current state, but it just plans one step at a time. So the second option says the algorithm plans one action at each step. This is true. The training instance contains example state and the best. No, this is not true, right? Because what I told you is based on whatever action it is choose, we assign some reward or punishment, right? So we let it explore whatever it wants to do, and then we assign some reward to it. The algorithm groups unseen data based on similarity. This is clustering. This is not reinforcement learning. So the second option is most appropriate one. Okay, Vanijan, you can type it out, whatever doubt you have. Okay, okay, I'll just try to throw some more light about reinforcement learning. See, I'll just give you an example of a child. So that's the best example to understand reinforcement learning. So when you were a child, you started to walk probably at an age of 1.5 or something like that. When you were learning to walk, what you used to do probably is you would have held something and tried to stand first, right? So while standing, there might be many instances when you tried standing, but you could not stand because probably you were not using the correct laws of physics. So nobody taught you like what is gravity, how much force is required, what is required, but you figured it out on your own. How did you do that? You tried something, right? And based on that, either you succeeded or you failed, right? So sometimes you were able to stand, sometimes you were not able to stand. So something similar to that, we let an machine learning algorithm uh, explore different actions that it can take. Right? For a like self-driving car, when we train it on a program, so what we do is we present scenes to it, right? So we presented some picture to it. What action should it take? It can either apply brake, let's say. It has only two options possible: apply brake or keep moving. So sometime the car might crash, or sometime it might go smoothly, right? When the car crashed, then the algorithm would learn that in this kind of situation, I should have applied brake. So from next time, it will try applying brake in those kind of situation. So this kind of setup is what is called reinforcement learning. Now is it clear? Like you take decision on every step, and based on your decision, you get some reward, like the way the environment is changing. Based on that, you get some reward, and that reward is something that you try to maximize to get the final uh, trained model for this reinforcement learning. Is it clear, Vani? Even if it is not, you can just say that it is not. Okay, I'll move ahead. So next question is, you are given reviews of few movies marked as positive, negative, or neutral. Classifying reviews of a new movie is example of, I want you to answer this question, you all to answer this, what it is. Like you have to classify whether it is supervised, unsupervised, semi-supervised, or reinforcement learning. Yeah, it is a supervised learning, right? So one thing I think that I probably missed is something called semi-supervised learning. I'll just tell you what it is. So, like data is quite expensive, right? Data is not freely available everywhere. So, and that too, when you look at label data, that is very scarce. Like you have lots of photos of dogs online, but you don't have anyone who has like assigned label to them that this is a photo of dog. Like not much data is available that is labeled, right? So what is semi-supervised? It uses both like supervised as well as unsupervised to leverage out of them. What it is, I'll just say. Let's say you have something like this, and there are two groups that are formed, right? Two groups that get formed. So one is this, one is probably this, right? So two groups. I'll come to that question, Ravina, after this. Just wait a minute. Okay, so if two groups are formed, so an unsupervised learning can very well like bifurcate that are two groups being formed. Now, let's say you hire some person just to label one of these data, and he said that this is a dog. Then what does it mean? This complete group of photos are dogs. So we got our result just by using one of the label data, and other data set even being unlabeled, we were able to infer about them. Similarly, if somebody labels something over here as cat, then this complete data set we can call them as cat. So this kind of setup is called semi-supervised setup when we leverage out of both supervised as well as unsupervised learning. Okay, so this is something that I missed earlier. This is it. Okay, so what's your question? Sir, why not it depend on the current situation? It depends on the current situation. That is what I'm saying. But it does not plan action like more than one step at a time. So when you are a child, you first try to stand. You straight away don't focus on running. So you take one step at a time. This is what I'm saying. Not actually. It is not necessary. So this is just a broad overview of what semi-supervised does. So it is not necessary that we do unsupervised always first. So there can be a lot of techniques that probably would be covered later in this course. So you can have combination of both. So you can also do them parallelly. So it is not necessary. Okay, so these are some questions, but I'll skip because I think I'm spending too much time on this. So I'll move to the next topic that I thought to cover. So like you would have gotten flavor what a machine learning algorithm is by viewing at the lectures. The reviewers are categorical feature. Yeah, review you give it in stars, right? So 1 star, 2 star, 3 star, 4 star, 5 star. Action. So yeah. So next is like a generic framework of a machine learning algorithm, but this is not again exhaustive. This is just a general model that most of the algorithm follow. So right now I'm sticking to supervised learning because most of the common algorithm right now that is used these days are supervised in nature. Okay. So what you have initially, you have some feature vector and corresponding label. So what I mean by feature vector, I'll just say, let's say you want to find rate of a house, then what kind of information you will give? You will give the size of the house, number of bedrooms, okay, and location. So these kind of information you need to give about a house. So this is called feature of like a single data point. So this is what is captured by xi, and the corresponding label is captured by yi's, right? So this is so when you try to build a machine learning algorithm, what you initially will do is you will split this data point uh, into two sets, right? Right now, just take it that you'll split it into two sets. One is your training data, another one is testing data. So using the training data, you train a model, and testing data you hold for some time. Okay. So let's go to this branch, like what we will do with training data right now. Okay. So with the training data, you will try to minimize some loss function. One is, and you can just type it out in the chat. Like you need not raise your hand. You can type it in the chat. I'll read it. I'll come to what is loss here, right? So it tries to minimize some kind of loss. Okay, so what we want to do is we want to find a function f that should take as an input xi and should output yi. But getting an accurate function is very difficult because you don't have one data point, you have many data points. And you want a function f that should fit to all these data points at one time. Okay, so let's say I'll just draw an example. Let's say you have something like this. You have these data points and you want to fit a line through all of them. So there is no possibility that a single line can pass through all these points. So the best estimate would be something like this. This line would be a best estimate that can estimate all these 3 points. So you want to find the best estimate. So what the best estimate would do is it would minimize the loss. What kind of loss? So it will take distance from this line to these data points. We will sum these distances and we want to minimize this distance. Okay. So this notion of loss function will vary from task to task that I'll come to. But in general, what we try to do is we try to find a good function f. Okay. That should kind of approximate these values, right? Now again, if you look at this example that I gave you, you might say that this line cannot fit, but this curve can very well fit this data point, right? So we impose some restriction on what kind of function we can allow. So the second week that you have is on linear regression. So in linear regression, you allow only straight lines to fit through the data points. Why do we do so? We will come to that towards the end today, right? So we will just try and fit some specific type of curves. So we can allow, let's say, a polynomial of at most degree 2, right? So what kind of functions that we are allowing, that is called the hypothesis space. Okay, so this is the select. Now let's say we have trained some algorithm. We trained using whatever thing that you will learn in next week. That hasn't been taught to you right now. So that you will learn in next week. So you know that you have trained something. Now what's the role of this test data set that you held? So you trained something on your training data. Now you like hide something from this training structure, and you want to test on this kind of data set whether it is good enough to deploy in real world or not. Let me take an example of this self-driving car again. So let's say you trained a self-driving car, right? You trained the self-driving car, and it was doing very well when you were training it in the computer, but in real world it crashed. You don't want that thing, right? So you want to test it on some data that it has not seen before, some situation that it has not seen before. So driving car can't see every situation in the world. So it will come across many new sceneries and it need to act on that also, right? So so this thing is called testing. So this is why testing data is helpful. So you can test it on the testing data. It is if it is performing well enough on that, you can deploy it in real world. Still, there is a possibility that it might fail on the real world data, but this is what we most of the time do. Now I'll come to what a loss function is. Okay. Now this notion of loss function varies from task to task. Okay. Now let's say we have a regression. Okay. In regression, we want exact value, I'll input the length, breadth, and everything of a house. I want the price of a house. Let's say it's $100K. Okay, something like this. So if we are making some error, what kind of loss would be good for a point? We can take absolute value of like whatever we are getting as predicted value minus what we should have got. So we can take a difference between them. So this can be a loss function. We can take square of the difference. I'm just trying to make these things positive. That's why I've taken modulus over here and square over here, right? So these are two possible candidates for loss function. Akshay, I'll come to that also, but probably towards the end of the lecture. So hyperparameter tuning is not relevant right now because right now no algorithm have been taught to you. So most of you might even not know what a hyperparameter is. Okay. F of xi is your predicted value. I'll come to this validation set in a while. F of xi is your predicted value, right? So yeah, so this is your loss function. So these are the possible loss function that you can have for a regression. You can also have something like power 4, or there are other variants of this also. So this depends on kind of data set that you have, or the kind of problem that you're working on, right? So kind of problem that you're trying to solve. So this loss function will vary based on that. But two of the most common loss function for regression is this. Now, if you look at this, this is something like a squared loss function. So this you might have solved in your 12th class, or if somebody is in masters, then you might know how to minimize this kind of loss functions. So that's one thing. Now for classification, there are a list of loss functions that I wanted to cover. First is this 0, 1 loss function. Now what does this 0, 1 loss function says? Like if this is your predicted value, f of xi is what this machine learning algorithm is predicting, right? So if the machining is predicting exactly same what, I'll come to the confusion matrix. I have not reached there yet. So this f of xi, if it is predicting exactly well as this actual label that was available, this yi is the actual label, then we assign loss to be 0, because whatever we wanted machine to do, the machine is doing exactly same as what we wanted it to do. If it is not doing what we wanted it to do, then we assign an error of 1. This is just for one data point. Okay. So across data point, we can just sum the loss function. And in some application, you can also average this loss function. So this is another loss function. Now, how to minimize this, how to optimize this thing you will learn in the next week's content. Professor Sudesh. Okay, so this was one of the loss function for classification. Another important thing to like tell you about how your classification algorithm is performing is a confusion matrix. Okay. Now, I'll just try to explain what a confusion matrix is. So this across this horizontal domain, right? Here I have written the ground truth that was available to me. So if it was positively labeled, I have written P over here. And actually, if it was negatively labeled, I have written N over here. Now, across this vertical line, this is the predicted label. So whatever this model predicted for us, that is your P and N across the vertical line. Now, what does this true positive mean is that ground truth was true, it is positive, and the model also predicted positive. So it is true positive, right? What is this false positive? That ground truth was negative, but your model actually predicted it to be positive. So it is misclassifying it. So this is a misclassification. This term over here is a misclassification, right? So here also this is a misclassification. Actually, it was positive, but algorithm gave it as negative. This is something that algorithm is giving to. So if we look at these 4 values, this gives us a very good idea how an algorithm is performing. Okay. So this is something what is a confusion matrix. So confusion matrix is not a loss function, but it helps us get many loss functions. Okay. So accuracy is another kind of, it is not a loss, but it is sort of inverse of loss. We try to maximize our accuracy. Okay. So if you look at accuracy, what it would be like, wherever it classified it correctly. So correctly is true positive plus true negative divided by your like whatever was possible. This is total number of data points. So this is what your accuracy is. Now there are 2 more terms associated with it, that is your precision and recall. Okay. So I'll just want you to read this question first, then I'll move to precision and recall. Okay. So it says, that during the treatment of a cancer patient, the doctor needs to be very careful about the patient that need to be given chemotherapy. So like if you are giving chemotherapy to a healthy person, then it is not a very good idea to, like, it is harmful for his health. Okay. So what right now you are doing is you are using a machine learning algorithm to decide upon whether you should give that person a chemotherapy or not. Okay. So, okay, Bani, if you know, that's fine. Right. So I'll explain what it is. So what you want is that if a person is not actually suffering from cancer, not having cancer, then that person should not be given chemotherapy. Okay. That's what you want. So what kind of metric you should use to ensure that a person who is not having chemotherapy should, like not having cancer, should not be given chemotherapy. So I'll just come to definition of precision recall, because it is asked like whether it should be precision or recall. So what precision actually means intuitively is like, let's say I'll take cancer's example only. If the machine learning algorithm says that the person is having cancer, okay, so what is the chances that it actually had cancer? So it is somewhat vague. I'll just make it more formal, that it is the fraction of like data points that machine learning predicted true and they were actually true. Okay. So the machine learning algorithm, if you see this matrix, predicted both these true positive as well as false positive as true. So what portion of like data points predicted true are actually true or positive? So this is what is something called precision. So it is true positive divided by whatever is predicted as true. Okay. So like it is true that you should try to, what should you try to minimize? You should try to minimize the precision over here. Okay. So you should look at precision in this case. This is not B, but actually A. So you should try to look at the precision that, like, if precision is high, then if the machine learning algorithm is saying that the person needs chemotherapy, then he actually needs chemotherapy. Okay. Now, what does recall means? Recall means how many positive example was this algorithm able to recover? Like out of actual positive examples, how many of them was it able to recover? This is what is called recall. Okay, so I'll like kind of stop about this topic. This is definition of F1 score, so you can have a look. This was not covered in lecture, but this is another loss function, or a not loss function, but a metric, not even a metric, but a like performance measure that is used. So Indranil, I think this question is from last year. I have included this question next. So I would want you to solve this. See, right now, whatever I mentioned, this true positive. So if this question is this year, then I won't solve this because that's a graded assignment. Thank you for letting me know that it's this year. Otherwise, I would have solved it next. So because you would get grades for that, I'm not allowed to solve your question. I can just give you an like layout how you should solve that problem. Okay. So you are asking that number of true positive should be maximized. Now, when you look at this true positive, this is with respect to positive class, this precision and recall, right? So you can also have similar precision and recall for negative class. Okay, I'll just come to the point. Okay, precision and recall for negative class also. Now, if you have something like digit recognition, then you can have this precision and recall for every class. That is your like class 1, class 2. Okay, so the question whether this true positive should be maximized is not actually true, because it would vary from the problem that you're trying to solve. So for example, over here, the person, like an example in medical domain, right? So here the person should maximize the precision rather than just maximizing the true positive. That too, this precision for a positive labeled class. So it will vary from problem to problem. So you can't say that one must try to maximize this. So one should try to maximize a combination of true positive and true negative, and also try to minimize false positive and false negative. So this is something that should be there. Okay, so this question I'm not covering. I have just very few minutes left with me, so I'll jump to bias and variance that I personally took a lot of time to understand. So I think I should first do this. Then I'll come to validation set as somebody asked. So, okay, so I'll just go to bias and variance. People still joining with 9 minutes left. So so if you see how a data point is sampled, okay, so this curve that you have, so you will have some true label, okay, so some true function, and you sample some points from that. Okay, this is how data sets are generated. There is some underlying distribution on which these points live, and you try to sample from that. So this is a sample from there, this is a sample. And while sampling, there can be also some errors. So this can be due to some apparatus or some machine that you're using, or due to some human carelessness. There can be some errors, right? Now let's say you have sampled such a data point, okay, and you are trying to fit a linear curve to it. Okay, so this would look something like this. Now, what is happening is, let's say you sampled once, you got these data points and you fitted a linear curve to it. This is what happened over here. Now you again sample. This time you will get some new points. Let's say you got these points here, here, these red ones that I'm drawing. So you got these points. Now you again fit a line through these points. Okay. So you will get another line. So here what I'm representing is there are 50 such instances when I have, not I, this is taken from a lecture by Professor Preeti Jyoti. She's from IT Bombay. So she has sampled 50 instances and she has tried to fit this linear curves to it. Okay. Now, if you look at real world data, when you go to collect data, it's not fixed which sample you would get, right? So two terms are of very importance to study. Those are bias and variance. Okay. To know like whether algorithm is good or bad, I'll just make it more accurate in a moment, right? So this was your true function. Let's say after taking 50 samples, 50 of this straight line, you take mean of these straight lines. Okay. Let's say this straight line is your mean straight line, something like this. So this mean straight line, mean prediction is represented here and it is denoted by g dash x. So how much is this g dash x varying from your f of x? This like how much is your g dash x? Yes, so we are 4 TAs. We all would be taking separate sessions. You can join any of them based on whatever time suits you. You can join even more than one, or you can try like all four of us, whatever sessions you are liking more, you can join that session. So it's not kind of a compulsion, but it's for your benefit. Whichever session you want to join, you can join. So we have placed it on 4 different slots because we want to give you more options. Like some of you might be working, some of you might be attending colleges. So time whatever suits you, you can join at that time. So bias is the difference between the average mean function and f of x, your true function. So this is not a bar, your true function. Okay. So now what I want to say over here is, let's say you sampled 50 times, still your mean function is very far away from this true function. If you see, this is a straight line and that's a curve. So it is very far away from the actual function even after sampling 50 times. So what does this suggest? That this straight line is not a very good fit to this. Whatever we are trying to do, this is not a very good fit. So we'll do something, try something like quadratic. Okay. Something like this might have been tried. This is not quadratic, but something like this would have been tried. So if your bias is high, so if you are getting a high difference or large difference between your mean function and true function, what you should know that your model is not capable enough to approximate these data points, like to fit to these data points. So this term that it is not capable enough is called underfitting. Okay. So what is underfitting is that your model is not advanced or capable enough to fit to the actual data. So this kind of scenario is called underfitting. So one phenomena, if your bias is high, that means you might suffer from underfitting. Okay. And what happens if your bias is low? You might suffer from overfitting. What is overfitting? I'll come to it in a moment. Okay. So because of want of time. So now you had this 50 points, right? These 50 straight lines. We have taken its mean. Next obvious thing to look at is your variance. Okay. So the variance of these functions that you are getting is called your variance for that like model. So this is a variance. This is just the expected value of this. Now, what's the implication of variance? I'll just try to show you. So let's say we took some 10-degree polynomial and we allowed 10-degree polynomial to fit three these data points. Okay. And it fitted something like this, which is drawn on left. Now, when we took another sample, what happened? These two data points got swapped. This point became this point became this. So now if you try to fit the function, this function would look something like this. Okay. Now if you see at the red line and the green line, there is lot of difference between these lines when you look at this region. So even with slight variation in this data points, I am getting two very different curves. Okay. So I'm getting two very different curves. So what does this mean is that the variance over here is very high. So do you want this kind of setup? We don't want this kind of setup. Why don't we want? Let's say we are like when we were trying to assign, when we were trying to create our data point. Okay. Then we made some small error in like assigning label to it, or we made some a small error in assigning feature to it. Okay. Then what this model will do is it will exactly fit to the erroneous data. So whatever data we had, even with the error, this model will fit to that erroneous data only. And in real world, when we'll deploy it on true data, then it will perform very bad. Okay. So this kind of phenomena is something called overfitting, that it is fitting very tightly to I'll come to it. It is fitting very tightly to your data points, right? So with as the variance increases, so you get overfitting. When your variance is very low, uh, that results in underfitting. Okay, this is something that happens. This is what you are. So this is a okay. So whosoever is joining for 7 o'clock session, so if you check the link, that's a different link. This session started at 6 o'clock and it would end in 5 minutes or so. So I request you to leave this session and join the 7 o'clock session. Some other TA is taking session over there. Okay, so this is the graph of bias and variance. So as you increase the uh, model complexity, what I mean by model complexity? By model complexity, I mean, let's say you're trying to fit some polynomial functions, then you're increasing degree of the polynomial function. Over here is something linear function. Over here is something called something like a 10-degree polynomial. So as you increase the complexity or you increase the like choice of your class of choice of your function, the bias will gradually decrease. Okay, but your variance will shoot up. So you want your model to be something around here. Okay, so you want it to be something around here. This is what I wanted to point out. So something, does low variance necessarily means high bias? So it generally does. Yeah, it generally happens. Okay, because like the data points that we are dealing with are sort of finite in sense. So when you are like very tightly bound, then your bias won't be very high because you are fitting very good to this. Next time also when you will fitting, you will be fitting very good to it. So on an average, so this graph is from under. I'll come to this. So this graph over here, if you look at this region, this is like underfitting. This portion can be called as underfitting. If your like allowed hypothesis space or the function that you're searching is in this region, this is overfitting. This is something a good reason where you should try to find your model in. Okay. Now there is one more graph over here. Okay. Now we are towards the end of our session. So if we have like there are two kind of errors that we see. Like I defined a lot of loss functions. Okay. Now you can evaluate these loss functions on test data as well as training data. So when you are evaluating it on training data, that is called training error. That is represented in red. And when you evaluate it on test data or the real life data, it is called the test error. Okay. So when we increase the model complexity, we see that the training loss is decreasing. Okay. So when you will train your model next time, probably in linear regression, so when you will take more and more features, your training loss will start decreasing. Okay. Or if you increase the complexity, you take x square, you take x cube also, your training loss will decrease. But when you look at test error, after a certain point, it will start increasing again. So we want our model to be in this region. And if you look at these two graphs, they have a similar kind of curve, right? So this region over here matches almost with the region over here. This is what I wanted to point. So here are some questions that you can see. What is the question? That why variance increase in overfitting like one self-fitted also? Difference should be less. Okay. Why variance increases? So the variance that you're looking at is, I'll again draw that example. Let's say these are some points that I had. You fitted it like this. Okay. Now the data that you're collecting is not very, I would say, accurate or the actual representation of world around you. So if you are sending someone to collect data, he might make some error. There might be like machines that might be making some kind of errors. So let's say that if this actual data was here and this data was here, then how would this graph look? This would look something like this. If you compare now this green and red curve, there is a large difference between these two kind of curves, these two curves. Now, if you were fitting a simpler function, let's say you were fitting a linear function, then for this red one, this would have been something like this. And for this green one, it would have been some, I'll use some other color, sorry. Okay, so for this red one, it would have been something like this. And for the green one, it could have been something like this. Again, yeah. So the difference over here is very less. Is very less when compared to when you are like fitting very tightly. So this is what I mean by variance. So it is overfitting. So when you are varying even single data point, then your function is fluctuating a lot. This is what I mean by high variance. So if you are moving even one data point, then your function that you are getting is changing a lot. This is what is meant by high variance. Is it clear, Akshay? Okay. So, that's fine. So you can now, like we have very less time, so you can just. So first question you all should attempt, like regarding bias and variance. So there can be more than one correct options also over here. Please tell me what options you think are correct. When we have overfitting, what do we have high? So when we have overfitting, we have high variance and low bias. Sorry, yeah, low bias. And we have when underfitting, we have low variance, high bias. Okay, so these two are true, I guess, yeah. So there are other questions also. From next time, I'll try to probably cover more questions. And so somebody asked about this validation thing. I'll try to look at that first because that's a doubt, and then I'll move to other things possible. So what is the idea of validation is, now I told you, like when you increase your model complexity, okay, model complexity, then your performance might increase, might decrease. Let's see this example. I'll come to the graph below. Just a second. So if you look at this graph, if you are in this region, let's say, then you should increase your model complexity a bit to get a better performance. If you are here, you should decrease your model complexity a bit. So there are other factors also called hyperparameters that you will probably learn from next week lectures. So another thing is, apart from model complexity, is hyperparameters. Okay. So if somebody is familiar with optimizations, so like if you use your gradient descent, so from a point you go alpha times the gradient at that point. So this alpha is also a hyperparameter. How do you choose this alpha? So how to decide upon the model complexity and hyperparameter? Okay. So this is one thing, like how would you decide? You can't deploy it in real world and then see, like if you are training some self-driving car, you can't leave it on road and see like it is performing well on test data or not. It would have killed many people by then. So for that purpose, what you do is you keep a small set for your small set called validation data. So now your data set would be split into three parts, right? So one is your training, next is your validation, and last one is your testing data set. Now what happens is you train on the training data, you yourself test on the validation data, and when you are satisfied, like based on this validation thing that you're getting, you choose this model complexity or different kind of hyperparameters that you have to tune, and then you deploy it in the real world. Okay. This is what the idea of validation data set is. Another thing that is important over here is sometimes data is scarce. Okay, you don't have a lot of data points with you. So then bifurcating a small portion of this validation set and keeping it apart and not using it for like training is not a very good idea. There we use the idea of cross validation. Okay, so what happens is you train your model in steps. Okay, so when you are initially training, let's say this is your complete data set, you have kept apart your test data set. This is test, just leave this alone. Okay, this is your validation thing. You train on this much portion. Now, next time when you train, you include this validation set in your training set. Rather, this time you choose another like set of data points, small set of data points for validation, and you train on the rest of these points. This test would remain like as it is. Okay, so this test thing would remain as it is. So what is happening this way is this data is being utilized for training next time, and you are also able to validate your things. So this idea is called cross validation. Okay. So this is the idea of cross validation that Professor Sudesh Sarkar also mentioned in the lectures. So whoever asked about this validation thing, I think this should be clear. And about hyperparameter tuning, that would be better to talk about it after you know, like what hyperparameter is. Some of you know what hyperparameters you encounter. So I think we are overshooting. So I won't go like discussing the other questions, but I'll stay here for around 5-10 minutes. Like if you have any doubt about anything that I discussed today or you watched in the lectures, you can just type it down. I'll try to answer like whatever I can. Anything that you want to ask about this. So whoever has joined after 7 o'clock, this session will end right now. So it started at 6 o'clock only. So if you look at the announcement, you would have received different links with different timings. So I request you to leave this session and join the session that started at 7 o'clock. Somebody else would be taking that session. So this session is going to end now. So I request you to join that session. Okay, confusion matrix I'll do. See. Okay. So confusion matrix is for, first of all, two class classification. What do you mean by two class classification is what your, let's say you have, I'll call this function as f. This function f is your machine learning model. So what does this do? If you give it some input, it gives you some output. Okay, this is what f does. So when you have a function f, you give it some input, it gives you some output. In classification tasks, it can give you as positive or negative, that is true or false. So it can give you other examples also. Let's say you are doing image classification. It can tell you it is a dog or a cat. Okay. But you can mold this question as whether it is a dog or not. So if it is dog, it can give you 1. If it is a cat, it can give you 0. So 1 means true. This means false or positive or negative. So if you have two class classification, when you have to classify the data points, so this yi's that you are getting belongs to two of the class. It can be positive, negative. It can be true, false. It can be dog, cat. Then you can map it to 1, 0, right? Is this thing clear that if it is a two class classification, you can see that problem as a problem where you have to classify it as positive and negative or 0 or 1. Is this thing clear first? That when you have two class classification, okay. Now when you have two class classification, so this is for supervised learning only. So you have some xi and corresponding yi given to you. These things were given to you initially. Okay. Now, when you predicted these xi's, you got something else. Let's call it yi dash. Okay. Now you want to compare your yi and yi dash. How to compare that is through confusion matrix. Okay. Now how that is done, I'll come to that. So your confusion matrix has two rows and two columns. Okay. So this first column, so whatever is along this line, this horizontal line, so this first column, I write 1 over here and 0 over here, right? What does this mean is, this 1 that you see over here, actually the given label to that data point was true. So this actual label over here was 1. Over here, 0 means the actual label was 0. Okay. Now along this vertical line, okay, this is the predicted label 1 and 0. Now I'll give you an example. Okay. Let's say this is some xi. Corresponding to this, I had some yi given. Okay. So this was some, let's say 10, this is 1, this is 11, this is 1, this is 5, this is 0, this is 6, this is 0. This was my x was given to me and yi was given to me. Okay. Now I tried creating a machine learning model, and I used this machine learning model to give me prediction for this. What this machine learning model gave me was 0, 1, 1, 0. Okay. So corresponding to 10, it gave me output as 10. Corresponding to 11, it gave me output 1. Corresponding to 5, it gave me 1. And 6, it gave me 0. Now I want to fill in this thing. So tell me how many points the true label was also 1 and the predicted label was also 1. If you look at it, it was only at one place. So if you want to create a confusion matrix, the entry over here would be 1. And this quantity, that number over here, is called true positive. So true positive means it was actually positive and it was predicted as positive. Now here it is that the actual label was 0, but the predicted one was 1. How many of them are there? 1. This is called false positive. What does false positive mean? False positive means that it was actually 0. That is false. but it is getting predicted as positive. That is one. Okay. Similarly, you can fill in the other details. So this one is false and negative, and this is true negative. Now, is it clear what a confusion matrix is? Whoever asked this. Like whatever part is not clear, you can just type it, or I'll try to elaborate more on that. Sumanti, okay, it is clear. So anybody has any other doubt? Anything that I have covered today? No. If not, then I'll end this session today. Okay. Thank you all for joining. I'll stop